Hello everyone, my name is Iftekhar Uddin Ahmed and my metric number is 820EC3016, and today I'm excited to present my thesis on comparative analysis of machine learning techniques for flash flood prediction. This work was supervised by Asset Professor Dr. Siti Zaitun at University of Technology Malaysia. So flash floods are among the deadliest natural disasters known for their sudden occurrences and extensive damage they cause. Accurate prediction of these floods is critical for timely evacuation and reducing economic losses. Today, in my presentation I'm going to cover six topics: introduction, literature review, research methodology, research design and implementation, results analysis and discussions, and conclusion. As mentioned earlier, flash floods are one of the nature's most deadliest phenomena. So, according to research, a natural catastrophe like flash floods which kills over 20,000 people each year and cause significant damage to infrastructure and agricultural systems. Asia accounts for over 90% of global flash flood fatalities. Flooding in Asia might nearly be doubled by 2050, according to projections. Each year, flash floods are responsible for thousands of deaths worldwide, especially in regions with poor infrastructure. The unpredictability of these events makes them particularly challenging to manage. The primary aim of my thesis is to assess and enhance the accuracy and reliability of flash flood forecasts using advanced machine learning models, contributing significantly to disaster management efforts. My research is focused on three main objectives: integrate and analyze comprehensive meteorological data, including rainfall and temperature variations, develop and implement several machine learning models, specifically artificial neural networks, random forest, and decision trees to predict flash floods, evaluate these models based on accuracy, precision, recall, and F1 scores to identify the most effective technique for real world application. The scope for my thesis are to collect combined data. We will use sources like temperature and weather data to gather comprehensive information. To construct useful patterns, we will go through the data sets and identify the critical elements that can predict potential floods accurately. To inquire into the performance of the random forest based approach, artificial neural network based approach, and decision tree based approach. In reviewing the current landscape, I analyzed various studies that employed traditional and modern techniques in flood prediction. This review highlighted the significant gaps in current methodologies, particularly in handling multidimensional data and real time processing. This gap underlines the necessity for innovative approaches that can dynamically adapt to changing environment data and capability intrinsic to machine learning. This study's methodology is divided into several sections. First, I collected extensive datasets from meteorological sources. Following this, I preprocessed the data to ensure quality and consistency, which included handling missing values and outliers. The data was then split into training and testing sets to evaluate the models objectively, simulating real world conditions as closely as possible. For the performance measurement, we'll be using accuracy, precision, recall, and F1 score. So, accuracy is the correctness of the system's classification, and precision is the reliability of the system predicting a flash flood. So, for calculating accuracy, we will be doing true positive plus true negative divided by true positive plus true negative plus false negative multiplied by 100. And for precision, we'll be doing true positive divided by true positive plus false positive. The fraction of factual flood events detected by the model is called recall. For recall, we'll be doing true positive divided by true positive plus false negative. And F1 score is the general metric that combines both precision and recall, balancing them out perfectly in such cases where the costs of false positives and false negatives are very different. For F1 score, we'll be doing 2 multiplied by precision multiply recall divided by precision plus recall. This is a dataset, and for dataset, we actually have a vast dataset that contains a lot of features, but we'll be not using all the features, and we'll be selecting out a few features like maximum temperature, minimum temperature, annual rainfall, and the drainage area for our feature selection. This is the flowchart for the data pre-processing. So here we'll be starting first. We'll be detecting where the null value is present or not, and then if the null value is present, then we'll be handling missing values. If the null value is not present, then we'll be going to the remove outliners. After that, we'll be splitting the dataset, and then we'll save, and then we'll end the process. This is the pre-processed data. So for the train data, we took uh, 80%, and the test data, we took 20%. Now, for the results and analysis, first we have the artificial neural network. So here, the ANN displayed high precision of 0.94 and good recall of 0.87 for class 0 non-flash flood, and indicating its effectiveness in recognizing true negatives for class 1 flash flood, while precision was slightly lower at 0.89. The recall was excellent at 0.895. Showing strong sensitivity in detecting actual flood events, the overall accuracy was 0.90. For the confusion matrix, the ANN predicted 349 true negatives and 372 true positives, with relatively few false negatives, 25, and false positives, 54. This indicates a strong ability to correctly classify both flash floods and non flash flood events with a low rate of misclassification, particularly in identifying flash flood accurately. So for the ROC curve, the NN exhibits an area under the curve of 0.96, showcasing excellent model performance. The curve climbs steeply towards the upper left corner, indicating a high true positive rate and a low false positive rate, which are desirable traits for effective classification in critical applications like flash flood prediction. The basic unit of an ANN is the neuron, which receives inputs, processes them, and generates an output. The behavior of a single neuron can be described by this equation over here, where xi are the inputs to the neuron, wi are the weights assigned to each input, b is the bias term, f is an activation function such as sigmoid, tanh, or well u, which introduces non-linearity to the model. So now we have the random forest. The random forest model exhibit balanced precision and recall across both classes with slightly better performance than the ANN. It achieved a precision of 0.93 for non-floods and 0.91 for floods, with corresponding recalls for 0.89 and 0.94. These results indicate that the random forest model is highly adept to classifying both non-flood and flood events with a balanced accuracy. Now, for the confusion matrix, the random forest model shows a slightly better performance than the ANN with 351 true negatives and 374 true positives. The numbers of false negatives is 23 and false positive 54, 52 are lower than those in the ANN model, indicating an excellent balance in predicting both classes with higher accuracy on few errors. Now, for the ROC curve insights, the area under the curve of 0.96 of random forest model indicates very high performance, as observed with the ROC curve positioning in the upper left corner, suggesting a good trade-off between true positive rate and false positive rate over different thresholds. So a random forest combines of multiple decision tree to improve classification or regression performance. Each tree in a random forest outputs a class prediction, and the class with the most votes become the model's prediction. The prediction for regression is the average of the predictions from all the trees. So now for the decision tree model, while effective, demonstrated slightly lower performance compared to the random forest model. Both precision and recall for non-flood and flood events were uniform at 0.85 and 0.87 respectively. With corresponding F1 scores, this uniformity suggests that the decision tree model is consistently fair but lacks the higher discriminative power of the random forest and ANN models. Now, for the confusion matrix analysis for decision tree, the decision tree model, while effective, has higher numbers of false negative, which is 45, and false positive, which is 64, compared to the both ANN and random forest models. It predicted 339 true negatives and 352 true positives, reflecting a competent but slightly less reliable performance in distinguishing between the two classes. So for the RC curve insights, the decision tree model represents an AUC of 0.86, which is lower compared to the NN and random forest models. The curve approaches the diagonal more than the other models, indicating higher false positive rates at various threshold levels, while still showing good capability to differentiate between the classes. The decision tree model's performance suggests that there is actually room for improvement in terms of accuracy and reliability. The decision tree splits the data into branches to form a tree structure. Each node in the tree represents a test on an attribute. Each branch represents the outcome of the test, and each leaf node represents a class label. The path from root to leaf represents classification rules in a simple binary tree. So the node split, saturation, S equals to argmax S and I parent. So here I is an impurity measure, and n is the total number of samples at the parent node, and left and then right are the number of samples in the left and right branches. S is a threshold for splitting the data based on a feature that maximizes the information gain. For the assessment of the model evaluations, the random forest model is the most reliable and balanced for predicting the flash flood. Its high accuracy and balanced precision and recall make it ideal for practical use. The artificial neural network also shows strong potential with good performance and significant predictive power, though slightly less than the random forest. The decision tree model, while useful, might need further improvement or combination with other models to be more effective. And yeah, in conclusion, this study has demonstrated the potential of machine learning techniques to revolutionize flash flood prediction. The insights gained here could be pivotal for disaster management authorities to enhance preparedness and response strategies. So, moving forward, integrating real time data streams and further improving the model adaptability will be crucial for advancing prediction. Maybe in the future, we can also add images and deep learning for enhancing the prediction. Thank you for your attention. I appreciate the opportunity to share my work with you, and I am open now, ready for any question to answer.